Today, we're going to begin a new chapter that is work and energy. We're going to start by the introduction now. This person is pushing a wagon. Note that the wagon is under the action of the energy dispensed by the person. So when the person moves the wagon, he is spending energy. This energy is able to move the wagon. This energy is revealed because there is an applied force and a displacement of the wagon. The force acts on the wagon in order to move it. This transfer of energy into a force and movement is called a work. The work of the force F. Thus, the work of the force F appears in the wagon by a force and a displacement. Assume that after a certain duration of displacement, the person leaves the wagon. The wagon is going to decelerate. What are the forces acting on the wagon? We have its weight mg, Rn, and the force of friction. But which force is responsible for the wagon's deceleration? It is the friction that opposes the displacement. Mg and Rn don't have an effect on the displacement, so we say that these forces don't do a work. All forces that are perpendicular to the displacement, this is the displacement for example, all forces that are perpendicular to the displacement have a work equal to 0. The force F is responsible for the deceleration. This force possesses a resistive work because it will resist the motion or oppose it. Moreover, if the person was unable to move the wagon, displacement wouldn't exist. Then the work of the force wouldn't exist as well. A force whose point of application is fixed, that is to say, it can't lead to displacement, and hence its work becomes 0. So if the point of application of a force is fixed, the work of this force is 0. Imagine that the person pushes the wagon over a long trajectory. Then the person will dispense more and more energy, and hence the work of the force F will be greater. Then the work of the force F is a function of the displacement. If the person exerts a greater effort, that is to say he will dispense more energy, and as a result the work done by the force F will be greater. Then the work of the force F is a function of the force itself as well. In this part, we're going to find the expression of the work done by a constant force when its point of application moves over a certain segment. Note that the force here is constant. What is the significance of a constant force? A constant force doesn't change its direction or magnitude during motion. We say that this force is constant. Here it is making a certain angle with the direction of motion. What is the work of the force by definition? The work of the force F when its point of application moves from A to B. Of course, we're not interested in the energy being dispensed, but we're only interested in the work. So what is this work equal to? The work of F when its point of application moves from A to B is equal to. We know that the work is a function of the magnitude of the force F. So when F increases, then the work will increase as well. So it is equal to F multiplied by the displacement, where the greater the displacement is, the larger the work. So it is F times AB. But we must add something. If the force is perpendicular to the displacement, that is to say, if theta is 90 degrees, then the work is 0. So we have to add cosine theta, where theta is the angle between AB and F. When theta is 90 degrees, F is perpendicular to AB. That is to say, cosine 90 becomes 0. So the work of F is 0. Then in this case, we notice that the work of F can be written as the scalar product of F dot AB. In the above scalar product, if the two vectors are perpendicular, the work of the force is 0. AB is the displacement vector, or simply the displacement. AB is the displacement. If F is perpendicular to the displacement, the work is 0. If the displacement is 0, the work is 0. As F increases, the work will increase. And if AB increases, the work will increase as well. So the work done by a force is the product of the magnitude of the force by AB by cosine theta, which is the angle between AB and F. The work done by a force F when its point of application moves from A to B is F times AB times cosine theta. This is the displacement, this is the force. F is in newtons, AB is in meters, and the work is in joules in the SI. Let's take several examples. Application. Assume that we have a body that is moving under the action of several forces. This is F1 of 10 newtons, and this, for example, is F2 of 14 newtons. This is F3 of 20 newtons. And this is F4 of 60 newtons. Take this angle to be 60 degrees and this one to be 40. On the wagon, we have two additional forces. These forces are its weight, mg, and the reaction of the support, Rn. The wagon moves from point A to point B. We need to find the work of each force when the wagon performs a displacement from A to B. This displacement is equal to 40 meters. Now let's use the previous expression. What is the work of F1 when its point of application moves from A to B? It is F1 multiplied by the displacement, that is AB, which is the covered distance in this case, times cosine of the angle between F1 and AB. Now pay attention here. This is F1, and this is the displacement. This is the positive direction. F1 forms with the displacement a certain angle. Then this is F1 and this is the displacement. the angle between F1 and the displacement is 0 in this case. So we have the magnitude of F 100 times 40 times cosine 0, which is 4,000 joules. So the work done by F1 is 4,000 joules. Now to continue. The work done by F2 when its point of application moves from A to B. It is F2 times AB times cosine of the angle between F2 and AB. This is equal to 40 times 40 times cosine of the angle between F2 and AB. Or it is the angle between F2 and the positive direction. In this case, it is 60 degrees. And the answer is equal to 800 joules. Now for the work of mg, the weight. The work of mg when its point of application displaces from A to B is equal to 0, since mg is perpendicular to AB, which is the displacement. Similarly, the work done by Rn from A to B is equal to 0, since Rn is perpendicular to the displacement. All forces that are perpendicular to the displacement have no work, since they do not have any effect on motion. Now for the work of F3 when its point of application moves from A to B. This is equal to F3 times AB times cosine of the angle between F3 and AB. And this is equal to 20 multiplied by 40 multiplied by cosine of which angle? This is the direction of the displacement. The force is opposite to it. The angle between these two vectors is 180. So we write here cosine 180 degrees. The answer is negative 800 joules. We're going to talk about this negative sign later. Now for the work of the force F4 when its point of application moves from A to B. It is F4 times AB times cosine of the angle between F4 and AB, which is 60 times 40 times cosine of a certain angle. Look here. The angle between the positive direction and F4, this is the positive direction and F4, how much is it equal to? This is the positive direction. This is the angle between F4 and the positive direction. This angle is equal to 180 degrees minus 40 degrees. The answer for this is approximately negative 1840 joules. We have obtained two types of work, a positive one and a negative one. This work is positive, and you obtained another one that is negative. F1 and F2 act along the direction of motion in one way or another. The work of these two forces for example, is motive. F3 and F4 act in opposite directions of motion. Their work is negative, so their work is resistive. Resistive work, motive work. The motive work is that of motive forces. The resistive work is that of resistive forces.